Welcome, detectives. My name is Jason Richards, Microsoft Technical Trainer and Data Detective. Our investigation centers around Delta Lake, an advanced storage layer that enhances data reliability, security, and performance. By leveraging ACID transactions and data versioning, Delta Lake ensures the highest level of data integrity, while simplifying both batch and streaming processes. As we delve deeper into this case, we'll discover how Delta Lake integrates seamlessly with the Databricks platform, providing the perfect toolkit for solving complex data challenges. Prepare your magnifying glasses, detectives, as we decode the case of the Delta Detective. Before we dive into the Lakehouse itself, it's probably good to understand what it is. A Lakehouse serves the function of a data warehouse, but leverages the cost-effectiveness of object-level storage as the data layer. The first clue we need to understand is how the underlying data is saved. In a typical database solution, SQL pages are created. In the Delta Lake solution, Parquet files are created. Both contain headers that describe the data in the page or file. The main difference is how the data is formatted. In a typical database solution, data is row optimized, where a Parquet file is columnar optimized and compressed by default, perfect for big data analytics. Now let's look at the difference in how transactions are logged. In a typical database solution, a temporary database stores the transaction logs. In a Delta Lakehouse, a Delta log folder is created along with the Parquet files and contains JSON log files that hold the transactional changes. The combination of these data structures, along with the optimistic concurrency built into the Delta API, allows ACID compatibility and the ability to time travel back to previous table versions. Now that we understand the underlying data structure, let's start creating Delta tables. One of the easiest ways to create a Delta table in Spark is to save a data frame in the Delta format. For example, the following PySpark code loads a data frame with data from an existing file and then saves that data frame as a Delta table. The code specifies that the table should be saved in Delta format with a specified table name. Once executed, the metadata for the object is saved in the metastore, and the underlying data for the table is saved in Parquet files along with a Delta log folder containing the transaction logs for the table. Since we didn't identify a file path to land the underlying data, the table is saved in the default catalog. You can also use the Spark SQL API to create these objects as well. Here, we're specifying a schema and referencing the data location to load the data table. We can create tables where we would prefer the underlying data to be stored externally. This is called an external table, and is created simply by defining a file path where we want the underlying Parquet files and Delta log to be stored. While it is possible to create external tables utilizing the Unity catalog, you'll need to establish a connection to the external location to the Unity catalog before creation. External table behavior differs from Unity catalog and the Databricks file system. Now you may be asking, what's the difference between a managed and external table? Let's take a look. When a table is created, two parts are saved. A table definition, which is the metadata or pointer to a table, as well as the actual data and those associated logs. When creating a managed table, the table definition and the underlying data files are both saved and managed by the Unity catalog. Deleting the table will also delete the table definition and data from the Lakehouse. When creating external tables, the table definition, while still in the metastore, directs or maps to the data, which is stored in an alternative file storage location. This means that deleting an external table will remove the table from the metastore, but does not delete the underlying data files associated. This approach can be useful when you want to create a table definition that references data that has already been saved in Delta format, or based on a folder where you expect to ingest data in Delta format. Certain scenarios may require you to save data in Delta file format as opposed to a Delta table, which essentially prevents a table definition from being created. This approach can be useful when you want to persist the results of a data transformation performed in Spark in a file format over which you can later overlay a table definition. It's also good to know that you can still get the benefit of a transaction log that is saved with the file. There may also be scenarios where you want to save the table definition that could be used to populate tables later. You can use Spark code to accomplish this as well. Probably not much of a shocker, but you can work with Delta tables or Delta format files to retrieve and modify data in multiple ways. The most common way to work with data in Delta tables in Databricks is to use Spark SQL. You can embed SQL statements in other languages, like PySpark or Scala, by using the spark.sql library. For example, the following code inserts a row into the products table. You can also use native SQL statements. You can either use Spark SQL as the default language in a notebook, or use a magic operator that will override the default language in a notebook. Here, we're updating the products table by changing the price of a certain product. Another option is to use the Delta Lake API. You can create an instance of a Delta table from a folder location containing the files in a Delta format, then use the API to modify the data in the table. Here, we're defining a Delta table object in memory and updating the prices of all accessories. This will update the file without persisting a table in the Lakehouse. Yes, detectives, time travel is possible, but not in the sense you might be thinking. Modifications, like updates made to Delta tables, are logged in the transaction log for the table as a JSON file. Each JSON file serves as a version of the table. Because of this, we can use the log transactions to view the history of changes made to the table and to retrieve older versions of the data, known as time travel. To see the history of a table, you can use the describe SQL command as shown here, and the results of the statement show the transactions that have been applied to the table. To see the history of an external table, you can specify the folder location instead of the table name. You can retrieve data from a specific version of the data by reading the Delta file location into a data frame, specifying the version required as a version as of option. All the data we've explored up to this point has been static data files. However, many data analytics scenarios involve streaming data that must be processed in near real time. For example, you might need to capture readings from Internet of Things or IoT devices and store them in a table as they occur. But where do we store the streaming data? And how do we query it? Let's dive into the clues. A typical stream processing solution involves constantly reading a stream of data from an input, optionally processing the data through various queries or functions, and writing the results to an output. Spark includes native support for streaming data through Spark Structured Streaming, which is an API that is based on a boundless data frame in which streaming data is captured for processing. A Spark Structured Streaming data frame can read data from many kinds of streaming sources, including network ports, real-time message brokering services such as Azure Event Hubs or Kafka, or file system locations. In the following PySpark example, a Delta table is used to store details of internet sales orders. A stream is created using the read stream method that reads data from the table folder as new data is appended. After reading the data from the Delta table into a streaming data frame, you can use the Spark Structured Streaming API to process it. Here, the data frame is simply displayed, but you could use Spark Structured Streaming to aggregate the data over temporal windows, for example, to count the number of orders placed every minute, and send the aggregated results to a downstream process for real near-time visualizations. Let's dig in a little further. In the following PySpark example, a stream of data is read from JSON files in a folder. The JSON data in each file contains the status for an IoT device. So the fields we're collecting from the JSON file would be the device and status. New data is added to the stream whenever a file is added to the folder. The input stream is a boundless data frame, which is then written in Delta format using the write stream method to a folder location for Delta table. You may also notice the checkpoint path indicated in the code. The checkpoint location option is used to write a checkpoint file that tracks the state of a stream processing. This file enables you to recover from failure at the point where stream processing left off. After the streaming process is started, you can query the Delta Lake table to which the streaming output is being written to see the latest data. Streaming data is boundless, so when a structured streaming job is submitted, it won't stop unless you programmatically stop it. Keep that in consideration when executing notebooks or scripts that contain streaming functions. Now that we've gathered clues on how to work with Delta tables in Fabric, let's connect the dots and put this knowledge to practice. Yes, we're jumping back into the DetectoLab 5000, aka my Surface laptop. The game is afoot.
Welcome back, detectives, to the DetectoLab 5000. And we're going to solve the case of Delta Lakes. Now, there's been a little setup that I've done in the background before we started this, just to make things go a little bit quicker. What I've done here is I've set up a couple of catalogs or a couple schemas, schemas in here called Delta Lake. Within this, we got a device stream and then we got people. Now we're going to create a streaming, a table that updates through streaming sources, and we're going to create a table that, just a static table that we're going to manually update using the Delta Table API. So a couple different ways that we're going to work with this. When you get into like Delta Live tables, this is how we can automate this process. So you'll see how manual this is. And then when we get into Delta Live tables, you can see how much easier it is to set up pipelines to do this for us. So I'm going to be using the default schema and the Delta Lake schema. The default schema is going to hold on to my static data, so to speak. I'm just going to create a table, update it manually, and then we'll check the updates and view the history and do some other things to it. And then we'll get into the streaming part. So let's hop into the notebook and get this going. Also under the catalog, it's probably good to note that under this people volume, I have a CSV file that we're going to be utilizing for this first part. And then when we get into the second part, I'll show you where all this other data is going to land. So the first thing we need to do, obviously, is create a table, right? So what we're doing in this first cell is and I'll execute it because it's going to take a little bit of time, is I'm defining a schema, defining the catalog name, where the schema and where the file is, that export file, from that, from the catalog, the schema, and the volume that I've created. And then we're going to create a data frame from this. And from that data frame, we're going to write to a table called people10m. Now, if you remember from the content, if we don't define a file path, this is a managed table. And with the Unity catalog, setting up external tables is a little bit more process-oriented because Unity catalog is set up for governance and security. You need to establish connections with your external sources before you can define external tables using this. So we're not going to really create external tables here. Just remember that this is a managed table, so if I delete the table, the data is going to go with it. If it's an external table to some other source, even the DBFS in this case, then if I delete the table, the data is still there. All right, now what we're going to do is we're going to upsert. So we're just going to merge and insert data, some additional, 6 additional rows to this data itself. So I believe that this data frame, and let me just run a display on this. so that we can see the underlying data. This should have 1,000 rows in it, right? So what we're going to do is we're going to upsert this. We're going to add 6 additional rows to this. And the way that we're going to do this is we're going to create the rows first, right? We're going to create the same schema here. We're going to add rows to this. And then we're going to create a data frame out of this, call that people 10M updates. And then we're going to create a temporary view called people underscore 10M underscore updates. Now we're going to use what's called the Delta API. Now this is a way that we can Pythonically work with Delta tables. Now you could use, since we have these in views and we already have a table created, you could use SQL commands too. And for some of this stuff, we'll show you that you can interchange between SQL and Python if we need to, or PySpark in this case. But this Delta API allows us to do things like perform merge and update operations, delete operations, your basic CRUD type operations for the tables that you want to do. So essentially, we're going to add 6 rows to this table, right? So I'm taking the original table, and then we're taking the people updates and then merging that with the existing stuff where the ID column meets the ID column, right? So there should be 6 additional rows to this. And if I read people 10M, you can see that where the ID is greater than that. So I can tell right here that the data has been updated because there's 6 additional rows. If I did the DF filter, or if I just loaded in the data frame itself, it should have 106 rows. So if I went back up here and let's run this again. Oh, that was the original. Nope, you can see it added the 6 rows to it. Now, because I made a change, that added a transaction. Now, in SQL, that would add it to the temp DB, and then we could do things like roll back or go to a previous version of the table. We're going to look at the history right now just to run the sanity check that, hey, I created the original table. And it shows what I did with it. It even gives the operation parameters for it. And all this is getting saved in the JSON log file that represents the Delta transaction logs. Same thing with the first version. So I know I have 2 versions now. What we're going to do is we're going to delete some data from the table. Using the Delta Table API again, we're going to delete any values or any rows where the birth date is less than 1955. Apparently, these aren't relevant anymore. So we're going to do that. So we should have another version, right? So let's display the table history again. By the way, you can use SQL commands to do this. I think it's just describe history for people underscore 10M in that case, right? Now, so you can see I have 3 different versions. This is all zero-based because we're using Python, and Python is zero-based programming. Spark is zero-based programming as well. What I'm going to do is I'm going to query an earlier version of the table. Now, there's a couple ways that you can do this. You can do this with a version as of, or you can do it with a timestamp because we have timestamp values in here. I'm going to do a version as of. You can see that I have version 1 in here, even though I've deleted some data out of this. What we can do is we can view the data originally. So let's look at the first version. And you can see that I have 1,000 rows in there. I can also view this from version 2. If we went back and did version 1 now, this is Pythonic version, you'd see I have 1,006 rows in here. So let's use SQL, so we can use a select star from people underscore 10M version as of 2. Right? And there should be significantly less because we removed any birthdays that were before 1955. So this is how I know that I can go back to previous versions of these tables. Now that's time travel. Obviously, if we're updating tables and all this is being held in memory and clusters and all that good stuff, we're going to have to optimize our formatting for this. If we append data or we add data to this, it's going to create additional Parquet files that stack up in the underlying files that represent the table. So what we might want to do after a certain period of time is optimize the table. So because we might have a lot of small files, what optimization will do is it'll take all those little small files and combine them into larger files to make it more performant, right? Another thing that we can do is use a method called Z-ordering, right? I would say it's kind of like a quasi adding an index, sort of. You could see we're doing this by a column. Since we're dealing here with people, we want to split the data up as evenly as possible. So the best way to do that probably is by using gender, right? So that'll split this up into male and female. So the Z ordering will just allow query operations to be more performant because now I'm creating these, quasi indexes on top of this. So it makes it a lot faster to look up this information. Also, when these updates are being performed, there's snapshots being created in the node, and we may want to clear out the memory from these snapshots. So you can also perform vacuum operations on the tables itself. By the way, you can do all this with SQL too. There's a optimize. There's a way to optimize tables using SQL. Same thing with Z ordering. Same thing with vacuum operations. So this will just clear up some memory. Probably some maintenance operations that you would want to consider when you're working with your tables in the real world. All we've done up to this point is work with the data in this catalog under this table. So if I expand this, you can see that the table's located here, and I can explore sample data within this. You can see there's 3 rows in here. There might have been a couple individuals that had their birthday before 1955 that might have been removed from this. But this doesn't show me all the data either. It only shows me a random sampling of 100 different rows, right? But I can definitely get some insight here from the Unity catalog itself. So that's static. So you can see there's some things that we need to do in order to update these tables. Now, what about the streaming side? So we're going to create a streaming process. The first thing that we're going to do is upload some JSON documents. Typically, streaming data is coming from applications, and applications typically have their data come in as a JSON packet. So that's what we're going to do. We're going to go ahead and create a file and load this file into a specified file path here in my catalog. So if I go back into my device stream, you'll see that this devices1.json file was added to it. Now, I say that we're going to show this in real time. Now, I'm going to update the table manually, but imagine, if you will, that all this data is updating consistently in the real world, right? So what's going to happen is I want to be able to read this data in, and I'm going to utilize what's called this read stream operation. So if you remember from the content, we perform a read operation just to read in static data. We use a read stream method to bring in streaming data. So this calls on the structured streaming library that's involved in Delta. So what this is going to do is it's going to consistently read from this file, right? So now I'm reading into it. I also want to create I don't know why that was running, but we're also going to create a process that is going to write back to this, back to a table that we're going to create called IoT data, right? So this is going to be the Delta streaming path, and this is going to be the 3-part naming system for it, but the table will be called IoT data. So it should land in the Delta Lake when I create this. So now when I go back in my catalog and I refresh this, Under my Delta Lake, you can now see that I have my IoT underscore data table that was created. And since this write stream operation is constantly running, it's going to continually add data to this. What essentially we're doing right now is performing a sanity check. You can see there's 9 rows in the data from when I perform this query operation on here. So what I'm going to do now is I'm just going to add an additional file to the path. So that's what this is going to do. In fact, this is going to be called devices2.json. We're just going to load that in. Now, keep in mind that when I created the original read stream operation, it's looking under the folder device stream, right? So under device stream now, if I refresh this, you can see that there's 2 files located in this, and it created that checkpoint location too for me when I did the write stream. I added a checkpoint path in here, which just happens to be in the same file path as the other stuff. So because I added that file and I'm constantly reading the data in and then writing it back to the table, what should happen is if I run another query, any additional data that's been loaded into this should reflect in another query. So you can see now I have 16 rows of data in here. So if you imagine this being real time, quote unquote real time, now that this other JSON packet has been loaded in, it's automatically, through this streaming, structured streaming, adding the additional rows to the data. So there's not much, so now I don't have to manually perform this operation. Another thing to keep in mind though is obviously if we have a streaming process that's taking place, whether we're reading it or writing it, you can see that this cell is constantly running. It's updating this table every 5 or 10 seconds, and you would be able to see the results from anything that gets loaded in here. If I don't want to perform this, obviously this is all going against my compute, and there's money associated with this. So if we don't need to update this table, then we can always just run this cell that will kill any streaming operations that are happening. All right, so you can see that now this isn't running anymore. Right, even though it still says streaming to data sync, that's just a print operation that we have, but this isn't running anymore. So I know that the process is stopped. But you literally have to stop a Delta stream in order to kill it. Now, if we're dealing with real-time data, we're obviously going to probably keep this running 24 hours a day, 7 days a week. But keep in mind that there's got to be a compute attached to this process. So either we're using one of our created clusters in here to run this, and then when you run like a Delta Live Tables pipeline that we'll show later on, you'll notice that that it runs through what's called a job cluster, and those job clusters just run on demand when the pipeline gets executed. So we're freeing up our all-purpose clusters for development purposes, and then you develop the pipelines and they run on a separate cluster, so we don't have to worry about creating them or defining them or using them in that context of things. But if you do want a more manual approach, and I think what this does is it really helps us solve the case of what Delta tables look like and how they get applied from a managed perspective. And then we want to go back and automate all these processes. So that's what we'll look at next. But as far as this case is concerned, we're going to call it closed. Let's move back into the studio.
Yes, fellow detectives, this is how we Delta in Databricks. Delta tables are a key component of the Lakehouse architecture, providing ACID transactional support and time travel capabilities. Whether you're investigating static or streaming data mysteries, Delta can help crack the case.